Hello, learners. Let me start with a thought. Have you ever cooked a dish where the recipe says heat oil, add spices, stir, then add vegetables? Notice how each step leads to the next, transforming raw ingredients into a final meal. Organic reactions are exactly like that, step-by-step transformations of molecules. Every organic reaction involves breaking and forming covalent bonds. The organic reactant is called the substrate, and the attacking species is the reagent. Together, they undergo a series of defined steps, sometimes producing intermediates along the way before giving the final product. Studying the mechanism means understanding how bonds break, how electrons move, and how intermediates shape reactivity. Once you know the mechanism, predicting products becomes as easy as following a recipe. Now, let's see how bonds break. Picture a tug of war. If both sides pull equally and let go, the rope splits into two equal halves. That is homolytic cleavage. The bond breaks evenly, and each atom takes one electron, forming free radicals. For example, when a chlorine molecule, written as Cl2, absorbs light, it splits into two chlorine radicals, each with one unpaired electron. These radicals are extremely reactive. On the other hand, if one side pulls the rope entirely, taking both halves, that is heterolytic cleavage. Here, both electrons go to one atom, forming ions. For instance, when a carbon-chlorine bond breaks, the carbon may lose electrons and form a positively charged carbocation, while chlorine becomes a negatively charged chloride anion. Carbocations are sp2 hybridized and trigonal planar, while carbanions are sp3 hybridized and pyramidal. Free radical reactions dominate in nonpolar conditions, whereas heterolytic cleavages lead to polar or ionic pathways. So always ask, are electrons splitting evenly or unevenly? Once bonds are ready to break, the key players enter, the substrate and the reagent. The substrate is the organic reactant, while the reagent is the attacker. Reagents can be electrophiles or nucleophiles. Electrophiles are electron-deficient species symbolized as E+, that seek electrons. Think of carbocations, the proton H+, or boron trifluoride, written as Bf3. Nucleophiles, on the other hand, are electron-rich species with lone pairs, hydroxide ion, OH-, cyanide ion, Cn-, or ammonia, NH3. They attack electron-poor centers. In mechanisms, we track them with curved arrows. The tail shows the electron source and the head shows the destination. For example, when hydroxide ion attacks ethyl bromide, written as CH3-CH2-Br, the electron pair flows from oxygen to carbon, pushing bromide out. That is the story of a nucleophilic substitution. It's almost like matchmaking. Nucleophiles donate electrons, electrophiles happily accept them. Now, the most artistic part of organic chemistry, the curved arrows. They are like Google Maps for electrons. A full-headed arrow means the movement of a pair of electrons, while a half-headed fishhook arrow shows the movement of a single electron. For instance, in resonance, you may shift a pi bond towards an atom, or a lone pair towards a bond, or push a bond between two atoms into one atom. These shifts explain why molecules are stabilized, why charges get delocalized, and why some pathways are favored. If you learn to read arrows carefully, you can predict whether the reaction is substitution, addition, or elimination. Remember, arrows don't lie, they reveal the exact journey of electrons inside molecules. Every organic molecule is influenced by electronic effects, just like how people react to push and pull forces. The inductive effect is the permanent shifting of sigma bond electrons due to differences in electronegativity. It decreases as you move away from the electronegative atom. The resonance effect, on the other hand, is the delocalization of pi electrons or lone pairs across conjugated systems. For example, in benzene, the 6 carbon atoms share 6 delocalized pi electrons equally, which stabilizes the ring. In nitrobenzene, the -R effect pulls electrons towards the nitro group. In aniline, the +R effect pushes electrons into the ring from the nitrogen atom. Then comes the electromeric effect, which is temporary. During an attack by a reagent, electrons shift completely towards one atom, common in double bonds like carbon equals carbon or carbon equals oxygen. These effects are the invisible strings controlling acidity, basicity, polarity, and reactivity. You could say inductive and resonance effects are permanent background music, while the electromeric effect is like a spotlight that switches on only during performance. Here's a fascinating advanced concept: hyperconjugation, also called no-bond resonance. Imagine hydrogen atoms next to a positively charged carbon lending their sigma electrons to stabilize the empty orbital. In other words, the sigma bond of a carbon-hydrogen overlaps with the vacant p orbital of a carbocation. This spreads out the positive charge, stabilizing the carbocation. That is why tertiary carbocations are more stable than secondary carbocations, which are more stable than primary, and the least stable is the methyl carbocation. The order is methyl carbocation less than primary carbocation, less than secondary carbocation, less than tertiary carbocation. Hyperconjugation also stabilizes alkenes and aromatic compounds. So even though we don't see these bonds directly, their invisible support makes the structure far more stable. Think of it like neighbors pitching in food when your kitchen runs out. The hidden support keeps everything balanced. So let's wrap it all up. Organic reaction mechanisms are the step-by-step stories of how molecules change. They involve bond cleavage, whether homolytic or heterolytic, electron movements shown by curved arrows, and intermediates like carbocations, carbanions, and free radicals. Reagents play their roles as electrophiles or nucleophiles, while electronic effects like inductive, resonance, electromeric, and hyperconjugation dictate reactivity and stability. With these tools, chemists classify reactions as substitution, addition, elimination, or rearrangement. And beyond textbooks, these concepts are vital in drug discovery, polymer synthesis, catalysis, and predicting product outcomes in labs and industries. So remember, once you understand the mechanism, reactions stop being a list to memorize and become predictable, logical, and even fun. Organic chemistry becomes less about mugging and more about storytelling with electrons. I hope this session made the invisible dance of electrons both clear and exciting. Catch you in the next class for more chemistry adventures.